Hey guys, it's Bryce here, and today we'll be talking about how to convert the Cartesian equation, right, uh, of a line to other forms of equations. Namely, we'll first convert it to parametric, and then we'll convert it to a vector equation. So if you can recall, right, the Cartesian equation looks like the form of this. So is the Cartesian equation is a equation relating the x, y, and z coordinates. Right? Then the parametric equation looks something like x equals to ax plus lambda bx, same thing for y, same thing for z, and the vector equation packages the Cartesian equation into a single vector notation. Like this, where the parametric equation and vector equation are actually very similar, just that the parametric equation takes each of the component and writes it like that instead of packaging it into a column. So today we'll be learning how to convert a Cartesian equation to a parametric equation. And so first let's do it numerically. So how do you do it numerically? It's actually rather simple. We just let this entire expression equals to lambda. Then from here, we make x, y, and z the subjects of the formula in terms of lambda. So for example, since ax and bx are constants that the question gives us, right? So from here, we know that x equals to ax plus lambda bx, and y equals to ay plus lambda by, and so on for z. And there we have it. We have the parametric equations. So that's how to numerically calculate. That's how to numerically convert the Cartesian equation to other forms of the equations of a line. But let's understand it from a geometrical perspective. So from the previous video, we learned how to interpret the Cartesian equation of a line in terms of 3 degrees of freedom minus 2 constraints. So what I mean by this is that from the Cartesian equation, you have 3 degrees of freedom, right? Which is the x, y, and z coordinates. At first, we're free to choose any x, y, and z we want. However, after that, we minus away 2 constraints. 2 constraints in terms of the equation. So 2 equations for 2 equal sign, because there's one equal sign here and another equal sign here relating the x, y, and z. Then after that, we are left with 1 degree of freedom, which is the degree of freedom along the line. So we can move along the line, choose any point along the line we want. So yeah, so geometrically, what setting this degree of freedom equals to lambda does is it allows lambda to be the choice along the line. So what I mean by this is that imagine we have a line, right? So we talked about revisiting what we talked about previously. We have the line, and one point on the line is located is identified by the position vector A. Then along the line, we have a directional vector B. And then if we choose, let's say lambda equals to 1, it'll be this point. We choose lambda equals to 2, it'll stretch B, right? Which allows us to walk along the line. When we choose lambda equals to -1, then it'll be going in the opposite direction. So this lambda represents the degree of freedom, and lambda can span from any real number between -infinity to infinity. And as vary lambda, right, we're walking along the line because the line has the form of r equals to a plus lambda b. So as we vary lambda across all real numbers, then our b will be stretched as much as the scaling parameter lambda, right? So it be stretched accordingly, and in so doing, we're walking along the line. So this was how we understood the vector equation. But okay, so why do we set this expression equals to lambda? Is because at this moment, right, the Cartesian equation, before having the lambda here, the Cartesian equation is is a is an equation of constraints. So basically, right, we were free to choose any value of x we want. So we are free to choose any value of x we want, but the moment we choose a particular value of x, all right, then the y and the z is automatically constrained because they must satisfy this equation. So as an example, let's say if set x equals to 1, then must be y must be equals to some fixed value, because x equals to 1 would mean that we have to solve for y, right? So so choosing a particular value of x would fix y and z, and likewise, if we choose a particular value of z, then it will fix x and y. But we can see that we can only choose, in any choices we make, right, we can only choose one variable before the two constraints take over and chooses the other two variables for us. So, so this degree of freedom, at first, we want to express this degree of freedom in lambda. And how we do so is that we're saying, by setting it equal to lambda, we are saying that, hey, instead of letting you choose a particular value of x, y, or z, right? How about I say I choose a particular value of lambda equals to this entire thing. So if by choosing a particular value of lambda now, right, we have shifted the choice, the freedom of choice from one of the variables, x, y, z, into this parameter lambda. So now I can choose any value of lambda I want, but the moment I fix one particular value of lambda, right, the other values of x, y, and z will be fixed by the equality. So now the degree of freedom, right, indicated by green, is no longer x, y, or z, right, is in the lambda. So for example, I choose, let's say, lambda equals to 1, then x will have to adjust accordingly, because then x will have to satisfy this equation, and to satisfy the equation, x will equals to ax plus bx, right? Or let's say I choose another value of lambda, let's say I choose lambda equal to 2, then x would have to equals to ax plus 2bx. But in any particular value of lambda that we choose, this degree of freedom, once we make a choice for lambda, x, y, and z is automatically determined, which corresponds to choosing, so the choice of lambda would correspond to um, creating, or rather fixing a point in space. Yeah, so the degree of freedom has now moved away from one of the choices of the x, y, and z coordinate to this parameter lambda. So that is what we are doing when we are setting the Cartesian equation equals to lambda. So yeah, so okay, so then what if that's clear, right, then let's go through a simple example. So, and then let's go through a trickier example. So let's say if x minus 1 over 1 equals to y minus 2 over 2 equals to z minus 3 over 3. So how do we convert this in, this is the equation for a line. How do we convert it into a Cartesian equation? We set it equals to lambda, and then this will give us x equals to 1 plus lambda, y equals to 2 plus 2 lambda, z equals to 3 plus 3 lambda. And this will give us r equals to 1, 2, 3 plus lambda 1, 2, 3. Yeah, okay, but let's say the question gives us another example where x minus 1 equals to over 1 equals to y minus 2 over 2, and then let's say they don't give us and let's say they say z equals to 3, okay, or let's say they say z equals to 5. So what do we do in this case? It seems like yeah, so in this case we will realize that z is already constrained, right? So in a so later so actually z is already constrained, so z equal to 5. Then for x and y, right now we have a degree of freedom for x or y, right? So that's where we set equal to lambda. Then we rearrange it to become x equals to 1 plus lambda and y equals to 2 plus 2 lambda. Then from here, we can have our equation. So this is, z is effectively 0 lambda. And from here, we can have 1, 2, 5 plus lambda 1, 2, 0. All right, so that's how you deal with the cases where the z, let's say, doesn't appear in this together with the y and x and y constraint, and instead the z constraint appears by itself. Okay, so that's just a example of a slightly tricky example that I've gone through. Thank you.